All right. Energy of phase changes. So keep in mind conceptually, if we're adding energy, we're going to be actually going to be endothermic, right? So going from endothermic, adding energy, exothermic coming down, exothermic coming down, going back, thinking about how energy is flowing into and out of the system. Now, when a phase of a substance is changing, there is no temperature change. This is often a misconception by many. It does take removal or addition of energy to make things happen. These can be called molar enthalpy of vaporization or fusion, or sometimes they're just called enthalpy of vaporization or fusion, and they're by mass instead of molar. Depends on the intermolecular forces holding the particles together. This is what's called a heating curve. And think about what the particles are doing here. As something is cooling or warming, if it's cooling, those bonds are slowing down from their vibrations, becoming slower and slower. If something's warming, those solids are now vibrating more and more, trying to overcome their intra or intermolecular forces, depending on if it's bonded or held together by intermolecular forces like sugar crystals are. Freezing and melting, you can see there is no temperature change when you have either of these phase changes, but you can see you have to add energy in to melt it or freeze it, remove energy. As a liquid, the particles moving around, increasing, warming, cooling, losing energy. Being familiar with the ideas of particle representations is often very present in AP Chem. So always think about when we see some actual occurring, think about what the particles are doing too and what that would look like. Condensing and boiling, same ideas, just different directions. Exothermic, endothermic. Now, one thing you might notice about any energy change is that thinking about these, we're overcoming intermolecular forces, some, or intramolecular forces, like bonds. As a liquid, you're still going to have these attractive forces, so there's going to be still quite a bit. However, to become a gas, you've overcome all forces. They're individual molecules very far apart. So when we have something boil or become a liquid to a gas, the amount of energy required is always going to be higher than it is to melt it. More forces to overcome in order to make it a gaseous form. Now, boiling point is a temperature at which the vapor pressure equals the atmospheric pressure. The idea is that if we have nothing around it, vaporization takes place very easily at the surface. They overcome the attractive forces and boom. When you have the vaporization rate higher than the condensation rate, you get it to vaporize. Once they're equal, this becomes an equilibrium and you'll have the vaporization stop occurring. It's kind of at a saturation point. One of the things I want you to keep in mind here is that boiling point can change based upon pressures. So the idea is that if you have a higher pressure above the liquid, the vaporization is going to stop at a certain temperature. So if you have less here, then it's going to vaporize at a lower temperature. Temperature, again, is just the kinetic energy of the particles. So if that's the case, higher kinetic energy can overcome those attractive forces or the particles that are above it. So keep in mind, boiling point is conditional, not just set by a substance. Now I mentioned molar vaporization or fusion. It can be either, again, as a molar sense or as a usual per gram sense. Again, when something melts or vaporizes, this is endothermic, taking energy in, exothermic, releasing energy. Try not to be fooled by the colors, okay? This is, again, the system getting cooler, the system getting warmer, not the surroundings. Also, again, think about the particle sense of what's going on as a solid, liquid, and a gas. Now, all of what we've been mentioning so far has been what's called enthalpy. That's thinking of the bonds breaking and forming. The other factor of energy is called entropy, this randomness of the universe. So I'd like to just kind of introduce this here, is that entropy, symbolized by a capital S, is that solids, as they warm up, will increase in entropy. Now I see this is introducing what's called a solid state phase change. This is what's calling the idea is beyond the scope of the course, but called polymorphs. A good example, chocolate has many different polymorphs. Sugar has many different polymorphs. Even ice has many different polymorphs. Same substance, different arrangement of the crystals. These would be present in covalent compounds where you have the solids that are arranged by different intermolecular forces and by different arrangements can have slightly different properties. But again, that's beyond the scope of our course. But with an increase in temperature, you have an increase in entropy. And you can see that these are the highest when we go from one phase to another. So as it melts, breaking those bonds, the randomness greatly increases. As it melts, as it is a liquid warming up, increasing kinetic energy, increasing the randomness. Similar idea that when we go from a liquid to a gas, that randomness of the particles increases. And you can again see these increases in entropy greatest going from liquid to a gas than it is from solid to a liquid. And even across the substances is generally very gradual and not as much as going through either phase change. Always goes from higher temperature to lower temperature, higher entropy to lower entropy. Again, we'll cover entropy a little bit later on, I think in Unit 9. But I wanted to introduce that concept here today. Now, I wanted to just kind of point out some things, given some values of heat of fusion, heat of vaporization, and their boiling points. All right. So we can see that the idea of something like going from a melting to boiling point, right? It may be small, 20, 30 degrees. It could be gigantic. Those differences are often looking at their ideas of heat of fusion and heat of vaporization being much, much higher. That makes sense. If you have strong intermolecular forces, like in ethyl alcohol, it's hydrogen bonding, you're going to have much, much higher heats of fusion and heats of vaporization. Again, ammonia also has hydrogen bonding. Again, you can see the difference is a little bit less, which makes sense for its heat of fusion to be less, and its boiling point to be much less as well, which results in lower heats of vaporization. Again, they're not always the same. This one has a 200-degree difference. This one only has a 100-degree difference, but a much, much higher idea of not only heat of fusion, but heat of vaporization. So again, comparatively, we know that something that has a higher heat of vaporization would have higher intermolecular forces. And of course, these are being nonpolar, which is going to have less. Also, the heat of vaporization is always going to be higher, much higher than the heat of fusion for one substance. What I like looking at is the metals, okay? The metals, this is pretty comparable to oxygen, right? Not too much energy, but you can see the melting point to the boiling point is huge. Now, you might think, well, what's the difference? I know these are bonded, and I know these are intermolecular forces, but these aren't that far off the weight of the compound. Oxygen is 32 grams per mole? Lead is 207.2 grams per mole. Way higher. Was that like 6 times higher? So it's going to require a lot more energy. Silver, iron, tungsten, much, much higher. And they also have different attractive forces. So once you get into something that's more sizable, you're going to have much more sizable amounts here. All right? But one thing to keep in mind is like looking at water, its heat of fusion is the most out of all of these, right? But its heat of vaporization is not the most here. So there's always a much more complexities going on. But again, some noticeable things, vaporization always higher than the heat of fusion. They're related, but they're not always the same ideas, that when you have liquid metals, those act differently than solid metals. Polar and nonpolar differ, but metals are very different. Also use the molar heat of vaporization if it gives it to you. Again, I think I use these gram ones because they're a little quicker, but on the test they can give you molar ones as well. So, how to solve these? Again, recognize mass and energies involved. You use these as conversion factors. Molar enthalpy or grams ones, just simple enough. This one again would show the idea of converting grams to moles. And again, these values would be provided for you, given to you, not memorized. And thinking about using your kilojoules also as well. can tell you the mass of water that's changed. So keep in mind, being used to converting kilo to regular or regular to kilo, think about how this would match. And again, your sig fig should match what you started with. Now, a very simple idea, mass of water that are required to essentially boil it. So you take the amount of kilojoules. Again, this is our kilojoules per kilogram on the previous page. Kilograms to grams. This is to be the mass of water to vaporize this amount of energy. Or I should say this amount of energy upon vaporizing would take, how am I saying this? This mass would require this much energy to go from a liquid to a gaseous state. Only to a gaseous state, not heated up, remaining at the same temperature. Energy is absorbed when ice melts. This one I've used the joules per gram value. Again, same idea. My mass, I use this as a conversion factor to see that it would require 5430 joules in order to melt 16.3 grams of ice. Now, these could be combined to go from solids to a gas. You remember our little heating curve? Well, that's what we're talking about here. When there's no phase change, you use specific heat. So when you're just heating or you got something solid, liquid, or gas, you use specific heat. If you wanted to figure it all out, to take something from like solid iron to 50 degrees above boiling, we can see what that would take. You would have your enthalpies for each of them. Or I should say you have your specific heat to get it to liquid, your enthalpy of solid to liquid, your specific heat to warm that liquid, enthalpy of liquid to gas, and then whatever temperature you have the gas. All of it's not very hard, just many steps. Units may change from joules to kilojoules, so they may need to be all the same in order to add together. So let's take a little example here. We've got a very cold piece of solid water, well below 0 degrees Celsius. One of the things that's often not thought about is that when you have something, ice freezes at 0, that doesn't mean that's always your starting point. Your freezer is often something where in negative 10 to 12 degrees Celsius, much below 0. That's why when you take something out, it doesn't immediately start to turn to water. It takes time to come up to that 0 degrees. And we want to heat it to gaseous water in a closed cylinder, very hot. So we need to go through our individual parts. Now our specific heat are different for different states of matter. You can see liquid's got the highest, while ice and steam are pretty close to each other. Now, using our specific heat, I'm going to start off first with warming our cold piece of water. So mass, specific heat, change in temperature. Change in temperature is going from our negative 13 to 0. I didn't bother writing that in. Let's say I made a couple adjustments with significant figures, so it's going to be rough. 2600 joules, not a bunch of energy. Melting it, so this is our heat of fusion, and even though we're not fusing something, same idea, it's the heat of fusion per gram. Quite a bit of energy, 10 times the amount to just melt it than it is to heat it. Keep that in mind. We're again heating the water, 0 degrees Celsius to 100. So to go up 100 degrees Celsius is almost the amount of energy it takes to just melt that same amount. Then we have the amount of energy required to vaporize it. Gigantic amount. And then we're heating the steam, another 90 degrees, very small amount. So add that all up, you get around roughly 290,000 joules. However, 200 of it comes from just vaporizing it. This shows the idea of the intermolecular forces being gigantic, okay? Which is why these other ones are overcoming some of those forces. And of course, even at a gaseous state, overcoming much, much less because, again, they're already very far apart as is. All right, so even though it's some calculations, they're not that hard. Just a little organization and addition is required. Come in with your questions. I'll talk to you later.